Hello everyone and welcome to our project presentation for our course project Renewable Energy System. Today my colleague Godfred and I, Muhammad Omar Shabir, will be presenting our work on design and simulate a grid connected PV system for MUN engineering building. And this project is supervised by under supervision by Dr. Tariq Iqbal. So let's start with the introduction and background. With global population growth, the need for reliable and sustainable and cost-effective energy system, uh, solar PV technology has emerged a viable option due to its scalability and environmental benefits. Our project explore how a grid-connected PV system can be reduce operation energy costs and the carbon footprint of one engineering building. Additionally, this project supports energy security, enhance community engagement through visible sustainability initiatives. In this slide, we will discuss about project site. In the figure, you see an aerial view for Faculty of Engineering for Oman University. Actually, this project site located in St. John's, which is capital city of Newfoundland and Labrador. This building is also known as Stanley James Carew Building, which houses the Faculty of Engineering. It's a multi-story building with substantial energy needs, primary due to they have a lot of laboratories, conference room, elevators, and interior lighting for the whole building. According to the facility management data, the building consumed about 3.67 million kilowatt hour in the year of 2023 by using tools like Google Map, or we are getting the data from the facility management. We assume that the rooftop area approximately 20,000 meters square for available for solar panel installation. The building load profile was developed based on occupancy patterns and daily operational schedules. Our next slide is about system sizing and simulation procedure. The design process included several steps. We started with the load assessment to understand demand. Then we designed the system and performed simulation using Homer grid. This was followed by steady state and dynamic modeling using MATLAB Simulink. We also addressed the control and protection system design to ensure operational safety and stability. Resources at project site. The slide shows the average monthly global horizontal radiance and temperature for the site. The environmental factors are crucial for determining the performance of PV system. For example, high radiance and moderate temperatures enhance energy generation, while extreme temperatures can reduce efficiency. In our next slide, site electrical data. After we getting the energy data, the building's annual consumption was approximately 3.67 million kilowatt hour. This figure was our baseline for determining how much of the load could be offset by a PV system. Our objective was to meet as much of this demand as possible with solar energy while ensuring grid connectivity. As per site data and characteristics, the facility management also provide an updated estimate the usable rooftop area, which came to about 19,954 square meter. After accounting for obstruction and shading, we aligned our load analysis with a university academic calendar to accurately reflect real energy use pattern. This helped us to optimize the system design. Here you can see the symmetric design of the proposed PV system. It includes solar array, inverter, and connection to the utility grid. The system allowed the efficient power generation and management, ensuring smooth integration with the existing electrical infrastructure. Canadian Solar 310 CS6X for 310 watt is a PV module employed in this work. It is a 60 cell monocrystal array of 310 watt maximum output. This maximum thus select the PV module suitable for direct grid connection. The solar PV's output DC voltage must be converted into AC to feed the building's load. The Shenzhen BYD BSJ 250K model power converter is used in Homer to perform this function. And as in previous slide mentioned, obtained load from faculty that is around about 3.67 kilowatt hour per year. If we will get this one by per day, it will be 10059 kilowatt hour per day. This is also optimization result and the winning situation, the system architecture, which we find in which Homer analyzed this one. It is this one. System production and consumption, which you can also set the simulation result. The main goal of this study is to design a grid-tied PV system that continuously supplies power to the MUN engineering building. No battery energy system were considered in this simulation, and the Homer optimizer feature is selected, which allow Homer grid to optimally select upper and lower limit for all components. As you see in the tables, the production of the different components for daily energy, for the energy production by yearly, and the percentage production also. So we this analyze that if we have a system with the panel three 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 hundred 3,513 kilowatt, which is round about which is equal to 11,333 watt panels, uh, which required area around about 18,500 square meter. But as per in my previous slide, as I informed you that what data we receive from the facility management, that they provide us the rooftop area around about 20,000 square meter, which is easily available that we can install it for there. And for inverter, the size we Homer suggests to us, it is 2,726 kilowatt, which is around about 11 inverters we required. And because each and one inverter we are using through 250 kilowatt. And this is the consumption for the log type, for the capacity percentage that the percentage consumption for the AC primary load, it is 67% approximately, and for the grid sale it will be 33%. This graph shows the simulated power output from the PV areas. As expected, output varies throughout the year due to changes in solar irradiance and weather conditions. Summer months summer months yields the highest output, while the winter months produces less due to short daylight hours. Financially, the system is viable. The total net present cost is $7.14 million. The capital cost, it is 5.3 million and the operating cost it is 1.69. The levelized cost of electricity is $0.101 per kilowatt hour, which is competitive compared to the grid electricity. So here we looked at the topics that how we make a load assessment and how we implement that load profile in the Homer Grid software and how we simulate the results and the cost analysis. So we will move on to our next topic for about dynamic and simulation in MATLAB and control safety operation are also performed, which is discussed by my colleague Godfred.
Hello everyone, my name is Godfred, and as my colleague Umair already mentioned, I'll be discussing this part of our project, the dynamic simulation of our grid-connected PV system. In this part of our project, we used a 2024 model of MATLAB to model and simulate our system. This picture here is an overview of the components and the connections we used to model and simulate our system. We have our PV farm here. The PV farm has two PV arrays, and each array is connected to an MPPT controller. The output of the MPPT controller is connected to this 3-level MPC inverter. The inverter is being controlled by this block here, the inverter controller. We have a step-up transformer which steps up the output of the inverter to 25 kilovolts. And we have a transmission line here, an 8-kilometer feeder, and the feeder is connected to the grid. We also have a step-down transformer which steps down the voltage from 25 kilovolts to feed our load. The load here is the MUN Engineering Building and is rated about 10 kilowatts. Inside our PV farm are our two MPPT controllers, as can be seen here. This is MPPT controller 1, MPPT controller 2. Each MPPT controller takes the respective voltage and current from its PV array and then uses the perturb and observe algorithm to vary the duty cycle of the boost converter to maintain an output power of each PV array to about 1.76 megawatt. Since the inverter's function in this project is to convert the PV's output DC voltage to AC, it requires a controller. The control method used in this project is to basically maintain the DC link voltage of the inverter at 1000 volts, regardless of the PV's output DC voltage. To achieve this aim, this block of the inverter controller measures and compares the DC voltage coming from the PV array to a reference voltage, which is the 1000 volts up here. The error voltage or the error signal is fed to this block here, these three blocks. These three blocks work together to perform the phase lock loop function. This function is to synchronize the PV's output voltage, which is AC, to the grid. So this block takes an input signal from the grid, that is the three-phase voltage and current signals, converts them to the DQ frame, and then compares the DQ frame voltage of the grid voltage to the error signal that was coming here. The aim of comparing is to reduce the phase errors, and 2, the frequency errors, and then the output is then fed to the transformer in our system. The foregoing were a description of the various components we used in our Simulink model. To start the simulation, we set some simulation parameters. The PV array's cell temperature was set to 25 degrees Celsius. Their solar irradiance was set to 1000 watts per square meter. 60 Hz was used as the system's frequency, and the simulations was carried out in discrete mode with a time step of 1 microsecond. The total length of the simulation was 1 second. Now, the simulations were carried out in two modes or two scenarios. The first was when there was no fault applied to the system, and the second was when there was a phase A fault, or when the fault was applied to phase A of the system. Now, this diagram here shows the irradiance, array voltage, and current of one PV array. On the left hand side of these two pictures, we see that the arrays each array's irradiance was set to 1000 volts, and to maintain the output power of about 1.756 megawatt, as can be seen here where the pointer is, the duty ratio of that array was adjusted such that it was about 0.45, and on the right hand side shows the output voltage and current of each PV array. The blue lines or the blue graphs here show the output voltage on the top and the output current of PV array 1, and the yellow, the same thing for the yellow, which is the PV array's voltage and current of the second PV array. We also see that the grids three-phase voltage and current were perfect sinusoids after the simulation when there was no fault applied to the system. This picture shows our inverter controller current in blue and our reference current in yellow. The inverter controller currents are the D-axis currents on the top part and the Q-axis current on the bottom part. It can be seen that we achieved a good inverter control because there's a minimal error between the reference and the control currents, because the reference current in yellow, you hardly see them, and that the controller currents in blue follow the reference current, and so we achieved a very good inverter control in our project. And again, this slide shows the inverter's output, which is typical of inverter's output waveform, which is good for our project. The foregoing graphs were for when the system was with no fault. Now we applied a fault at 0.25 seconds and we removed the fault at 0.45 seconds, and this graph shows the fault current. When the fault current was applied, the PV's output, this is the PV's output voltage, the power, the voltage, and the MPPT duty cycle. The PV's solar irradiance was maintained at 1000 watts per square meters. However, the power and the voltage changed in correspondence to when the fault was applied at 0.25 and when the fault was removed at 0.45. As can be seen here also, there's a waveform distortion during when the fault is applied for the current waveform and the voltage waveform. For the current waveform, it is seen that phase A waveform there's a spike in phase A waveform, or there's a sudden surge in the waveform when the current is applied, because we applied the current to phase A. And for the voltage waveform, it is seen that the phase A voltage waveform is reduced to almost zero when the current and the fault is applied. This shows that our system responds well to fault scenarios.
Regarding conclusion of this project, grid-connected PV system for MUN engineering building, which demonstrate feasibility of integrating large-scale solar power to institutional infrastructure. And we also observed that 71% of electricity demand of this building can be covered by this project. Which this project also contributes to sustainable campus operation and reduce carbon emissions. Regarding Homer, also analyze some cost analysis, economic analysis. The total net present for this cost, it is around about 7.14 million dollar, and the capital cost it will be 5.33 million dollar, and the operation cost it will be 1.69 million dollar. A levelized cost of energy, it will be around about 0.101 dollar per kilowatt hour, competitive with the grid supply. Also, we also simulate dynamic simulation of our project in MATLAB, which we concluded that it is stable operation under normal conditions, resilience during fault scenarios, for example, power recovery after fault clearance. And the last one, the system performance, the MPPT controllers ensure optimal power extraction from PV arrays. Inverter control system maintains DC link voltage at 1000 volt. This project also demonstrate protective capabilities during a single phase fault. Thank you so much for your time and your attention. And please, if you have any question, you can comment. You can ask in the comment section below. Thank you so much. Have a good day.